Welcome to an Introduction to Data Science with Python. This course is the first course out of 5 in a larger Python and data science specialization. Each course progressively builds on your knowledge from previous courses to give you a well-rounded view of what data science is while helping you to develop skills to practice data science. This specialization is of an intermediate level or difficulty, and we expect that you have studied some basic programming and statistics in the past. In this specialization, we're focused on teaching applied skills using the Python programming language. There are many other tools that one can use in data science, such as specialized statistical analysis languages like R, or more general-purpose programming languages like Java and C. We chose Python as the basis for this specialization for 3 reasons. First, it's easy to learn. Python is now the language of choice for introducing university students to programming and is used in 8 out of 10 of the US's top computer science programs. Python programs tend to have minimal templating that you might have seen in other languages and have more natural constructs for typical tasks you might need to accomplish. If you have programming experience but not Python-specific experience, you can pick up Python very quickly. Second, it's full-featured. Python is a very general programming language with a lot of built-in libraries and excels at manipulating data, network programming, and databases. It's mature and there's plenty of resources available from books to online courses. Finally, Python has a significant set of data science libraries one can use. The base of these is called the SciPy ecosystem, and it even has its own conference series. Both the interface that we're going to use for doing assignments, called Jupyter Notebooks, and the main libraries for the first 2 courses, Pandas and Matplotlib, are part of the SciPy stack and provide an excellent basis for moving into machine learning, text mining, and network analysis. This first course is broken into 4 modules. The first module focuses on getting prerequisites in place and reviews some of the basics of the Python language. Don't worry, if you already have Python down and you want to be challenged, we have some advanced Python in here as well. The advanced Python isn't strictly necessary for the rest of the specialization, but many of these examples you might see on the web or broader data science topics like big data and real-time analytics might require a knowledge of some of these more specialized features. In the second module, we're going to dig into the Pandas toolkit. The Pandas toolkit is a fundamental in Python data science and provides a data structure for thinking about data in a tabular form. This toolkit helps bring functionality that exists in R into the Python world and has seen significant adoption over the last 5 years. Much of the thinking behind Pandas is similar to relational theory, so if you have a background in databases, you'll find the Pandas environment fairly natural to work in. At the same time, some of the more advanced ways to query and manipulate Pandas data frames, like Boolean masking and hierarchical indexing, are different than in databases and require some careful discussion. So we'll discuss these in Module 3 of this course. The final module of the course is dedicated to the course project, where you'll take some data sets, merge and clean them, then process the data and answer some questions. In this week, we'll discuss basic statistical tests and methods and ensure you have a solid grasp going forward into the next course. At the same time, the intent is for your course project to be a demonstration of the skills that you've gained in manipulating messy data into something of coherence. Before we go into programming fundamentals, though, we'll talk a bit more about what data science is and why it's sweeping over the world. Hi, I'm Chris Brooks, faculty here at the University of Michigan School of Information. This class is about data manipulation. And data manipulation is really the foundation of what you'll do as a data scientist. And that doesn't really change even as you deepen a lot of your investigation and your skills in the area. So in this course, we're going to teach you the excellent Pandas library. It's wonderful for data manipulation. It is the de facto standard for Python. And when you come out of this class, you should be quite masterful in the use of that library. We're going to teach you about how to acquire data, how to clean data, how to manipulate and join data together, and how to make basic inferences about that data. Now, we expect that you already have some Python skills and some statistics skills, but this course is really a place where you're going to get to build those skills through practice. And there will be some course resources off to the sidebar in the course shell that describe other ways that you can get some experience with Python. I've filmed the lectures for this course in a very specific manner. I'm using a tutorial style where most of what you'll be watching is actually screen captures of me typing into Jupyter Notebooks code. And I'm doing a couple of unique things with this. One, you'll see all of my text, all of my comments in that code live. So you'll be able to read as well as listen. But I wanted to share with you a strategy that I think is powerful for learning and learning using the Jupyter Notebooks. And so let's take a look at some of the course shell right now. So this is the Coursera course shell here on the left. And on the right-hand side, I've opened up the Jupyter Notebooks. So this is actually a MOOC that I taught and I'm going to use to demonstrate. When you go to a video in the course, let's say this one on data frames, you'll see that it's a regular instructional video. I'll just mute that. And you can seek around in the video and there's some talking head. But the majority of it is going to look like this. Let's just close the notes and close the sidebar. The majority of it's actually going to look like this. It's going to be me working through examples in a Jupyter Notebook. And I think the most powerful way to learn in this course is actually to go into your Jupyter system. So I've got that here on the right-hand side. And there will be a separate video about the Coursera Jupyter platform. But to actually create a new Python notebook, it's empty. Maybe name it after the lecture. So this was data frames, I think. And to follow from the beginning what I'm doing and type it in yourself. So here we'll maybe seek to the beginning. And so here you can see I'm looking at some cricket-loving countries in this example. And so you could just type here cricket-loving countries and just follow the example as you go. The power of doing it this way is that at any time you can pause the video and you can explore and you can start to look at alternates and you can start to form questions. And this is really powerful to be doing as you're watching a video, to be actively learning instead of just watching passively this video. The video has a number of other opportunities in it. In particular, you can increase or decrease the speed of the video, and that can be useful too for review. I actually think high-speed video playback is wonderful. I listen to a lot of educational video this way, largely after I've already done the practice and I've already experienced it once, and I just want a quick review of the content. I'll flip it on at maybe 1.5 or 2 times speed and try and absorb that content. And the way we've built the videos for you for this class, which is frankly new to me and I'd love to get your feedback on, is with that whole transcript within the video as well. So you should be able to read and listen to the video at the same time. And you really can't go wrong with practicing over and over again. So please grab the educational videos as you're watching them, engage with a blank notebook, and just follow along and see how you've maybe misinterpreted things, different investigations that you've gone off on, and share what you found or questions you have with the rest of the class. Hi, I want to show you a little bit about the Jupyter Notebook system that we've built with Coursera into this course. It's a great feature. It lets you explore your assignments and your programming, the lecture content even, all within the web browser. I think it's really quite a wonderful addition to the degree, to our platform, and to your experience. So let's take a look. So this is what the Jupyter Notebook will look like when you log into it on Coursera. And at any time you can get back to this screen by clicking on the Coursera logo. And this is called the tree or the directory tree. And you can see here it's at /, which means we're at the root of it. And in this one, I've got 3 folders created, and I've actually got a text file here, a README markdown file. Now, if you want to create a new Jupyter Notebook, you just go over to the New button, click the little down disclosure triangle, and you can create a folder, text file, a terminal, we'll talk about that, or a new Python 3 notebook. So let's go ahead and create a Python 3 notebook. So this is the core of the Jupyter system, the Python 3 notebook. This single line here is called a cell. You can have two kinds of cells. You can have code cells and markdown cells. So let's just say x equals 5, print x, just something simple. So we can just write our Python in here. And then you can run this cell by hitting the button up here. And you can see we get the output right below the cell. You can move cells around, so we can move them up or down. You can delete, cut, copy, and paste, and so forth cells. So it's really handy. What's happening underneath is actually all of the code that you're writing is being sent to a virtual server that Coursera hosts, and it's being run against a Python interpreter there. Now, after you run a statement, it's not like just finished running a program. That interpreter still exists, and so the state still exists. So if we printed, for instance, x plus 1, that interpreter still knows what the value of x was, and so now we have 6. Up here in the upper right-hand corner, you'll actually see a reference to your Python interpreter state. It tells you here the kernel is idle. Let's try something else. For I in range 0 and 1,000. I equals, well, we won't do that. We'll just say m equals I times I minus 1. And we'll just run this. Now watch that little circle in the upper right as we run this. You see it very quickly flashed black, and that shows you that the interpreter is working. And so if you're looking at your system wondering why nothing is responding, take a look at that interpreter working. In fact, why don't we do something really nasty here? So why don't we just say for I less than 100, I equals 1. We'll just set I equal to 1 right above that. And we'll run this cell. Oh, this is a great example of some syntax error that comes up right here. We'll just change this to a while. All right, so this is an infinite loop, right? And we can see here that the asterisk here by the output actually tells us that the kernel is running. And we can see here the little black circle is filled in, showing that the kernel is running. If you get into this kind of state, you can just interrupt that kernel. It's like hitting Control-C on the keyboard. So you just say kernel interrupt, and it will just stop at any time. Other things you can do, you can restart the kernel. This is just like restarting Python. So actually, if we restart the kernel, and then we try and print x, we see that we get an error. You can clear the output, you can restart and run all, and so forth. There's lots of cell functions that you can do too. I often use this one, cell run all above. So I'll restart the kernel, and then I want to run all of the content of my notebook up until this point. If you want to switch to a cell to Markdown, you can do that. And then this is just regular text with a few extras. So if you want a big heading, and then you can do things like special text to bold it. And then when you run that cell, it'll actually render what the text looks like. And you'll see that in the notebooks throughout this course. Let's go back to the tree. In the tree, one of the other things you can do is actually open up a terminal. And this is pretty powerful. So you now have a terminal. You're logged in as the user Jovian. And this is just a Linux machine underneath. It's actually a virtualized Linux machine, a Dockerized one. And so you can do things like ls to take a list of the file system. You can do things like look, what is this untitled notebook? So if we wanted to look at that, cat untitled, and we can look, oh, it's just a giant JSON string and so forth. We can install new packages as well as needed. So you can use conda or pip to install new packages. Now, you probably won't have to use the terminal much, certainly not in this first course, but you should know it's there and be aware of its functionality. So we'll go back to the tree. The last thing that I wanted to show you in just this quick overview of the notebook is what an assignment might look like. And so if you load this assignment here, so this is just a sample assignment, you'll see that there's actually a rendered blue button here that actually submits it to Coursera when you press it. So that's how you'll submit the programming portion of the assignments. Now, we built into the assignments some unit tests to help you. And so as you're doing an assignment, you can hit the validate button, and it'll actually run some of those unit tests for you and give you an idea that, wait, there's a couple of cells here that need some work. Of course, when you go in and submit the assignment, you're also given this URL to go back and to look at the status of the assignment. So that's a really quick overview of the Jupyter Notebook system. Now, there's a lot of shortcuts, key commands, there's plugins that you can get for Jupyter. You can absolutely install Jupyter on your home PC or work PC or wherever you're doing this course from. But I think using it in this capacity built into the course is really powerful. The folder, the storage for your Jupyter Docker instance is on a course-by-course level, but you can download those files just from that tree. So there's an option to download files and move them around to other courses as well. I hope you enjoy this added feature of the course and the Coursera product, and look forward to hearing from you what you think of it. In the rest of this module, I'm going to provide a very basic overview of the Python programming language. If you have a background in programming, this overview should be enough to help you be successful in the rest of this course and the following courses in the specialization. If you don't have a programming experience or feel like content is overly challenging, then I would encourage you to stop and take an introductory programming class. A colleague of mine, Dr. Chuck Severance, offers an excellent specialization on Coursera called Python for Everybody. You can find a link to that in the course resources. The Coursera system allows you to run Python code from your browser in two ways. First, we can use in-video prompts, where a question will come up and you can try and solve that question in the browser. This is new to the Coursera platform, and we're going to try it in the next couple of lectures. Second, the Coursera system has been integrated with Jupyter Notebooks. These notebooks allow you to divide your code up into what they call cells and execute these cells on demand. The nice thing about these notebooks is that they offer a semi-permanent storage for your learning, and you can experiment and play with programming without having to install anything on your computer. All of the assignments will be done in the Jupyter Notebooks, but you can of course download and install Python, Jupyter, and all of the associated libraries you need for this course on your own computer if you'd like. Our tutorial assistant will provide an overview of this process by installing the Jupyter Notebooks locally in the next video for those of you who are interested, and I'll give an overview of how you can use these notebooks in the Coursera environment in this lecture. But for now, let's dig into some basic Python. First, Python is a high-level language, which means it's optimized for reading by people instead of machines. It's also an interpreted language, which means it isn't compiled directly to machine code and, importantly, is commonly used in an interactive fashion. This might be quite different if you're used to programming in something like Java or C, where you write your code, compile it, run it, and watch the output. In Python, you can start the interactive interpreter and begin writing code line by line, with the interpreter evaluating each statement as you write it. This turns out to be very useful for tasks that require a lot of investigation versus those that require a lot of design. Shell scripting is one example of these, and data cleaning is another. While you can write scripts that execute as programs like you might be used to in other languages, we're going to use Python throughout this specialization in this interactive fashion. A common surprise for some programmers coming from a Java or C background is that Python is a dynamically typed language, similar to languages like JavaScript. This means that when you declare a variable, you can assign it to be an integer on one line and a string on the next line. Since there is no compilation step, you don't have anyone to help you manage types. You need to either check for the presence of functionality when you go to use it, or try and use the functionality and catch any errors that occur. The dynamic typing of Python is particularly nice when used in an interactive fashion, as it allows you to quickly set and modify variable contents without having to worry about the underlying syntactic definition of the variable. Okay, so let's jump in with an example. For all of the code examples I'll show, you'll find an annotated version of the notebook with more comments in the course resources section. You're welcome to follow along with that if you would like, or create a new notebook and actively write code if you prefer. Python is very little boilerplate code. In fact, if you just wanted to set the value of a couple of variables and output the results of these variables added together, you could do so in 3 lines. In this example, I'll write 3 statements. The first 2 set the variables x and y, each to be some integer value. Then we'll do some addition. We can run this cell by hitting Shift-Enter, or by clicking on the playhead icon in the toolbar. The output from the statement is immediately printed. If you were using Python in a non-interactive mode, nothing would print, but since we're using it in an interactive mode, we get the value immediately. What's happening underneath is that the browser is sending your Python code across to a machine in the cloud, which executes the code in a Python 3 interpreter and sends the results back. We can see that after executing a cell, a new empty cell is created for us below. If we just put in x and execute, we get the value of 1. So it's important to know that the Python interpreter is stateful. That is, that your variables exist between cells. Beyond that, if we go back and change something in a previous cell, we have to re-execute the script to make those changes take place. The restart and run all function is particularly useful as it wipes the interpreter state and reruns all of the cells in the current notebook. You'll notice that Python doesn't require the use of keywords like var to declare a variable name, or semicolons at the end of lines, which are commonly used in other languages. Python leverages whitespace to understand the scope of functions and loops, and end-of-line markers to understand the end of statements. Of course, Python has traditional software structures like functions. Here's an example, refactoring that previous code into a function. You'll see the def statement indicates that we're writing a function. Then each line that is part of the function needs to be indented with a tab character or a couple of spaces. Again, because we're in an interactive environment, when the statement is evaluated on a Shift-Enter, the results are printed out immediately below. Here's our first bit of interaction. Why don't you try and change this function to accept 3 parameters instead of 2 and return the sum of all 3 of those? Okay, functions are great, but they're a bit different than you might find in other languages, and here are some of the subtleties involved. First, since there's no typing, you don't have to set your return type. Second, you don't have to use a return statement at all, actually. There's a special value that's called none that's returned. None is similar to null in Java and represents the absence of value. Third, in Python, you can have default values for parameters. Here's an example. In this example, we can rewrite the addNumbers function to take 3 parameters, but we can set the last parameter to be none by default. This means that you can call addNumbers with just 2 values, or with 3, and you don't have to rewrite the function signature to overload it. This is an important implication. All of the optional parameters, the ones that you've got default values for, need to come at the end of the function declaration. It also means that you can pass in optional parameters as labeled values. Here's an example of labeled parameters. We can rewrite that function so that there's 2 optional parameters. If we want to call the function with just 2 numbers but also set the flag value, we have to explicitly name and set the flag parameter to true when invoking the function. By now you've also seen the use of the print statement. We're going to dive into strings in more detail, but print will take an item, try and convert it to a string, and print the output. We don't use this much in the interactive mode of the interpreter, but it's useful when we want to print out multiple values for a single cell. Okay, a final word on the basics of functions in Python. In Python, you can assign a variable to a function. This might seem either completely normal to you or completely odd, depending upon your programming background. By assigning a variable to a function, you can pass that variable into other functions, allowing for some basic functional programming. We'll talk about that a little bit later on in the course, but here's an example where we define a function to add numbers, then we assign that function to a variable, and then we invoke the variable. That's a whirlwind tour of functions. Here's a poorly written one. Can you fix it? The absence of static typing in Python doesn't mean that there aren't types. The Python language has a built-in function called type, which will show you what type a given reference is. Some of the common types include strings, the none type as we've discussed, integers, and floating point variables. As we've seen, you can have references to functions as well, as a function type also exists. Typed objects have properties associated with them, and these properties can be data or functions. A lot of Python's built around different kinds of sequences or collection types, and there's three native kinds of collections that we're going to talk about: tuples, lists, and dictionaries. A tuple is a sequence of variables which itself is immutable. That means that a tuple has items in an ordering, but that it cannot be changed once created. We write tuples using parentheses, and we can mix types for the contents of the tuple. Here's a tuple which has 4 items. 2 are numbers and 2 are strings. Note here that I've used single quotes for a string, whereas previously I've used double quotes. In Python, either single or double quotes can be used to denote string values. Lists are very similar, but they can be mutable, so you can change their length, number of elements, and the element values. A list is declared using the square brackets. There are a couple of different ways to change the contents of a list. One is through the append function, which allows you to append new items to the end of the list. Both lists and tuples are iterable types, so you can write loops to go through every value they hold. The norm, if you want to look at each item in a list, is to use a for statement. This is similar to the for each loop in languages like Java and C#, but note that there's no typing required. Lists and tuples can also be accessed as arrays might in other languages by using the square bracket operator, which is called the indexing operator. The first item of the list starts at position 0, and to get the length of the list, we use the built-in len function. There are some other common functions that you might expect, like min and max, which will find the minimum or maximum values in a given list or tuple. Python lists and tuples also have some basic mathematical operations that can be allowed on them. The plus sign concatenates lists, for instance, and the asterisk repeats the values of a list. A very common operator is the in operator. This looks at set membership and returns a Boolean value of true or false, depending on whether one item is in a given list. We're going to dive more into operators and special kinds of sequences in a future week when we look at a technique called broadcasting. Perhaps the most interesting operations you can do with lists are called slicing. While the square bracket array syntax for accessing an element might look fairly similar to that which you've seen in other languages, in Python, the indexing operator allows you to submit multiple values. The first parameter is the starting location. If this is the only element, then one item is returned from the list. The second parameter is the end of the slice, and it's an exclusive end. So if you've sliced with the first parameter being 0, the next parameter being 1, then you only get back one item. This is much easier to explain with an example. One handy aspect of Python is that all strings are actually just lists of characters, so slicing works wonderfully on them. Here's an example. When we run x sub 0 or x sub 0:1, we get just the first character of the string. But when we run x sub 0:2, we get the first 2 characters of the string. Our indexing values can also be negative, which is really cool, and this means to index from the back of the string. So x sub -1 gets us the last letter of the string, and x sub -4, -2 reads in all of the characters from the fourth last to the second last positions. Finally, if we want to reference the start or end of the string implicitly, we can by just leaving the parameter empty. So x sub :3 starts at the first character and goes until position 3, and x sub 3: starts at the fourth character, because indexing always begins with 0, and goes to the end of the list. Slicing is core to the Python language and is a big part of the scientific computing with Python as well, especially if you start manipulating matrices. We're going to talk more about slicing in the next module, but here's a question to get you started. Now, I'm taking a bit of an aside here to talk about manipulating strings. Slicing isn't the only way to manipulate strings, and a common activity is to split strings based on substrings. That is, to go through the string looking for patterns and segmenting it as appropriate. This is called regular expression evaluation. We're going to cover this in detail in the section of the specialization which deals with text mining, since it's a very common operation. But Python has some basic tools for text analysis, and I'm going to show you them here. As we saw, strings are just lists of characters. So operations you can do on a list, you can do on a string. This means that you can concatenate two strings together using the plus operator, and multiplying strings will repeat a given string. You can also search for strings using the in operator. The string type has an associated function called split. This function breaks a string up into substrings based on simple pattern. Here, for instance, I'll just split my full name based on the presence of a space character. The result is a list of 4 elements. We can choose the first element with the indexing operator to be the first name and the last element to be my last name. We'll touch on strings just a bit more, but before we do, I want to talk about dictionaries. Dictionaries are similar to lists and tuples in that they hold a collection of items, but they're labeled collections which do not have an ordering. This means that for each value you insert into the dictionary, you must also give a key to get that value out. In other languages, this structure is often called a map, and in Python we use curly braces to denote a dictionary. Here's an example where we might link names to email addresses. You can see that we indicate each item of the dictionary when creating it using a pair of values separated by colons, that you can retrieve a value for a given label using the indexing operator. The types you use for indices or values in the dictionary can be anything, and this can be a mixture of types if you prefer. We can add new items to the dictionary using the same indexing operator we are used to, just on the left-hand side of a statement. You can iterate over all of the items in a dictionary in a number of ways. First, you can iterate over all of the keys and just pull the contents out as you see fit. Or you can iterate over the values and just ignore the keys. Finally, you can iterate over both the values and the keys at once using the items function. This last example is a little bit different, and it's an example of something called unpacking. In Python, you can have a sequence, that's a list or a tuple of values, and you can unpack those items into different variables through assignment in one statement. Here's another example of that, where we have a tuple that has my first name, last name, and email address. I declare 3 variables and assign them to the tuple. Underneath, Python has unpacked the tuple and assigned each of these variables in order. We can see that if we add a 4th item to the tuple, Python isn't sure how to unpack that, so we have an error. That's an overview of built-in types with Python. In the next lecture, we're going to revisit strings briefly, then start working with some data files. We talked about strings when we talked about lists and slicing, and you've seen ways to break up strings through the use of the split function and through direct indexing. Strings in Python can be a bit frustrating too, and I want to share some more details of how strings are handled so that you're aware of them. In Python 3, strings are Unicode based. In early computing, characters of strings were limited to one of 256 different values. This was enough to get all of the upper and lowercase Latin characters as well as single-digit numbers represented. This language was called ASCII and was fairly compact. But the world doesn't just run on Latin characters, and there's a need to support non-English languages, as well as characters which are not commonly used in words but are commonly used elsewhere, like mathematical operators. The Unicode Transformation Format, or UTF, is an attempt to solve this. It can be used to represent over 1 million different characters. This includes not only human languages, like you might expect, but symbols, like emojis, too. Python 3 uses Unicode by default, so there's no problem in dealing with international character sets. In addition to Unicode, Python uses a special language for formatting the output of strings. One of the challenges with dynamic typing is that it's a bit unclear when you have to do type conversion yourself. We saw in the last lecture that if we wanted to print out a name and a number, that we can't use concatenation without calling the str function to convert the number to a string first. This creates a lot of nasty looking code where every operator you're looking to concatenate is wrapped in this str function. The Python string formatting mini language allows you to write a string statement indicating placeholders for variables to be evaluated. You then pass these variables in either as named or in order arguments, and Python handles the string manipulation for you. Here's an example. Imagine we have purchase order details in a dictionary, which includes a number of items, a price, and a person's name. We can write a sales statement string, which includes these items, using curly brackets. We can then call the format method on that string and pass in the values that we want substituted as appropriate. Now, the string formatting language allows you to do much more than this. You can control a number of different things like decimal places for floating point numbers, or whether you want to prepend the positive numbers with a plus sign, or set the alignment of strings to left or right justified, or even enable the use of scientific notation. I've linked the documentation page in the course resources, and being able to use the string library and formatting language will be an important part of your first assignment. This has been a short lecture, but string manipulation is a big part of data cleaning. You're going to learn a lot more about string manipulation in this course through the assignments. In the next video, though, our graduate student assistant is going to show you how to bring some basic data analysis together through the reading and writing of delimited data files.
Welcome to today's tutorial, where we'll be learning the basics of iterating through a CSV file to create dictionaries and collect summary statistics. First, let's import the CSV module, which will assist us in reading in our CSV file. Using some IPython magic, let's set the floating point precision for printing to 2. Now let's read in our MPG CSV using CSV dict reader and convert it to a list of dictionaries. Let's look at the first 3 elements of our list. We can see that the dictionaries in the list have the column names of the CSV as keys, and data for each specific car are the values. The length of our list is 234, meaning we have a dictionary for each of the 234 cars in the CSV file. We can look at what the column names of the CSV are by using the key method. Suppose we want to find the average city MPG across all cars in our CSV file. We sum the city MPG entry across all the dictionaries in our list and divide by the length of the list. Because the type for all the values in our dictionary are strings, we need to convert to float to perform mathematical operations. Similarly, we can find the average highway MPG across all the cars in our CSV file. And it makes sense that the average highway fuel economy is higher than in the city. Now let's look at a more complex example. Say we want to know what the average city MPG is grouped by the number of cylinders a car has. Creating a set of the values in the cylinder entry of the dictionaries will give us the unique levels for number of cylinders. We see that we have cars in our dataset with 4, 5, 6, and 8 cylinders. First, we'll create an empty list where we'll store our calculations. Next, let's iterate over all the cylinder levels, and then we'll iterate over all the dictionaries. If the cylinder level for the dictionary we're on matches the cylinder level we're calculating the average for, we add the MPG to our sum MPG variable and increment the count. After going through all the dictionaries, we perform the average MPG calculation and append it to our list. To make things clear, I'm going to sort the list from lowest number of cylinders to highest. And we can see that the city fuel economy appears to be decreasing as the number of cylinders increases. Let's look at one more similar example. Suppose we're interested in finding the average highway MPG for the different vehicle classes. Looking at the different vehicle classes, we have two-seater, compact, midsize, minivan, pickup, subcompact, and SUV. Similar to the last example, We iterate over all the vehicle classes, then iterate over all the dictionaries. If the vehicle class for the dictionary matches the vehicle class we're computing the average highway MPG for, we add the value to our total and increment the count. Then we perform the average calculation and append it to our list. This time, let's sort our list from lowest MPG to highest. Looks like the pickup had the worst fuel economy and the compact had the best. So that was a look into how to summarize data through iteration. Don't worry if this seems somewhat inefficient or tedious. Next week, we will be learning about Pandas, a Python library that allows for easier, more efficient, and more powerful data analysis in Python. Thanks for watching. Hope to see you again soon.
A lot of analysis you do might relate to dates and times. For instance, finding the average number of sales over a given period, selecting a list of products to data mine if they were purchased in a given period, or trying to find the period with the most activity in online discussion forum systems. In this course, we're not going to delve too deeply into time series analyses, but I wanted to show you some of the basics in Python. First, you should be aware that date and times can be stored in many different ways. One of the most common legacy methods for storing the date and time in online transaction systems is based on the offset from the epoch, which is January 1st in 1970. There's a lot of historical cruft around this, but it's not uncommon to see systems storing the date of a transaction in seconds or milliseconds since this date. So if you see large numbers where you expect to see date and time, you'll need to convert them to make much sense out of the data. In Python, you can get the current time since the epoch using the time module. You can then create a timestamp using the fromTimestamp function on the datetime object. When we print this value out, we see that the year, month, day, and so forth are also printed out. The datetime object has handy attributes to get the representative hour, day, seconds, etc. Datetime objects allow for a simple math using time deltas. For instance, here we can create a time delta of 100 days, then do subtraction and comparisons with the datetime object. This is commonly used in data science for creating sliding windows. For instance, where you might want to look for any 5-day span of time where sales were highest and flag that for follow-up. This is just a little glimpse at dates and times in Python. In week 3 of this course, we're going to investigate dates and times a bit more using the Pandas datetime library. Up to this point, we haven't spoken much about object-oriented Python. While functions play a big role in the Python ecosystem, Python does have classes which can have attached methods and be instantiated as objects. Now, this course isn't about the nitty-gritty details of objects in Python or object-oriented programming. And actually, while you'll use objects a lot in Python, you're less likely to be creating new classes when you use the interactive environment because it's a bit verbose. But I think it's important to go over a few details of objects in Python just so that you aren't surprised when you see them. First, you can define a class using the class keyword and ending with a colon. Anything indented below this is within the scope of the class. Classes in Python are generally named using camel case, which means the first character of each word is capitalized. You don't declare variables within the object, you just start using them. Class variables can also be declared. These are just variables which are shared across all instances. So in this example, we're saying that the default for all people is the School of Information. It's not very useful here, but I wanted to show it for completeness. To define a method, you just write it as you would have a function. The one change is that to have access to the instance which a method is being invoked upon, you must include self in the method signature. Similarly, if you want to refer to instance variables set on the object, you prepend them with the word self with a full stop. In this definition of a person, for instance, we have written two methods, setName and setLocation, and both change instance-bound variables called name and location, respectively. When we run this cell, we see no output. The class exists, but we haven't created any objects yet. We can instantiate this class by calling the class name with empty parentheses behind it. Then we can call functions and print out attributes of the class using the dot notation common in most languages. There are a couple of implications of object-oriented programming in Python that you should take away from this very brief example. First, objects in Python do not have private or protected members. If you instantiate an object, you have full access to any of the methods or attributes of that object. Second, there's no need for an explicit constructor when creating objects in Python. You can add a constructor if you want to by declaring the _init_" method. Now, I'm not going to dive into any more into Python objects because there's lots of subtlety, and to be honest, most of the object-oriented features of Python aren't really all that salient for introduction to data science. If you're more interested, I'd recommend checking out the Python documentation from the Python tutorial. It's a fairly comprehensive overview of the object features of the language, and there will be a reference in the class resources. The map function is one of the bases for functional programming in Python. Functional programming is a programming paradigm in which you explicitly declare all parameters which could change through execution of a given function. Thus, functional programming is referred to as being side effect free because there is a software contract that describes what can actually change by calling a function. Now, Python isn't a functional programming language in the pure sense, since you can have many side effects of functions, and certainly you don't have to pass in the parameters of everything that you're interested in changing. But functional programming causes one to think more heavily about chaining operations together, and this really is a sort of underlying theme in much of data science and data cleaning in particular. So functional programming methods are often used in Python, and it's not uncommon to see a parameter for a function be a function itself. The map built-in function is one example of a functional programming feature of Python that I think ties together a number of aspects of the language. The map function signature looks like this. The first parameter is a function that you want executed, and the second parameter and every following parameter is something which can be iterated upon. All of the iterable arguments are unpacked together and passed into the given function. That's a little cryptic, so let's take a look at an example. Imagine we have two lists of numbers, maybe prices from two different stores on exactly the same items, and we wanted to find the minimum that we would have to pay if we bought the cheaper item between the two stores. To do this, we could iterate through each list, comparing items and choosing the cheapest. With map, we can do this comparison in a single statement. But when we go to print out the map, we see that we get an odd reference value instead of a list of items that we're expecting. This is called lazy evaluation. In Python, the map function returns to you a map object and doesn't actually try and run the function min on two items until you look inside for a value. This is an interesting design pattern of the language and is commonly used when dealing with big data. This allows us to have very efficient memory management, even though something might be computationally complex. Maps are iterable, just like lists and tuples, so we can use a for loop to look at all of the values in the map. This passing around of functions and data structures which they should be applied to is a hallmark of functional programming. It is very common in data analysis and cleaning. Here's a problem for you to try that brings together some of the tasks you might be expecting to do with data cleaning. You may have seen the keyword lambda appear in this week's content, and you'll certainly see it appear more as you spend more and more time with Python and data science. Lambdas are Python's way of creating anonymous functions. These are the same as other functions, but they have no name. The intent is that they're simple or short-lived, and it's easier just to write out the function in one line instead of going to the trouble of creating a named function. The lambda syntax is fairly simple, but it might take a bit of time to get used to. You declare a lambda function with the word lambda, followed by a list of arguments, followed by a colon, and then a single expression. And this is key. There's only one expression to be evaluated in a lambda. The expression value is returned on execution of the lambda. The return of a lambda is a function reference. So in this case, you would execute my function and pass in 3 different parameters. Note that you can't have default values for lambda parameters, and you can't have complex logic inside of the lambda itself because you're limited to a single expression. So lambdas are really much more limited than full function definitions, but I think they're very useful for simple little data cleaning tasks, and you'll see lots of examples with them on the web. So you should be able to read and write lambdas. Let's give it a try here. We've learned a lot about sequences in Python, tuples, lists, dictionaries, and so forth. Sequences are structures that we can iterate over, and often we create these through loops or by reading in data from a file. Python has built-in support for creating these collections using a more abbreviated syntax called list comprehensions. Here's an example. First, we write up a little for loop. Here I'm iterating between 0 and 1000 and then checking with the modulus operator to see if the number divided by 2 results in any decimals. If the modulus 2 of the number is 0, then I know it divides evenly, so this must be an even number, and I'll add it to our list. We can rewrite this as a list comprehension by pulling the iteration on one line. We start the list comprehension with the value we want in the list. In this case, it's a number. Then we put it in the for loop, and then finally we add any condition clauses. You can see that this is much more compact of a format, and it tends to be faster as well. Just like with lambdas, list comprehensions are a condensed format which may offer readability and performance benefits, and you'll often find them being used in data science tutorials or on Stack Overflow. But you're not required to use them in the assignments in this course. Here, why don't you try converting a function into a list comprehension?
Numpy is the fundamental package for numeric computing with Python. It provides powerful ways to create, store, and manipulate data, which makes it able to seamlessly and speedily integrate with a wide variety of databases and data formats. This is also the foundation that Pandas is built on, which is a high-performance data-centric package that we're going to learn more about in this course. In this lecture, we're going to talk about creating arrays with certain data types, manipulating arrays, selecting elements from arrays, and loading data sets into arrays. Such functions are useful for manipulating data and understanding the functionalities of other common Python data packages. So you'll recall that we import a library using the import keyword, and NumPy's common abbreviation is NP. So let's import NumPy as NP and import math. Right. Arrays are displayed as a list or lists of lists and can be created through lists as well. When creating an array, we pass into it a list as an argument in a NumPy array. So a equals np.array, and I'm just going to create a list here, 1, 2, 3, and we'll print out what a looks like. And we can print out the number of dimensions of a list using this ndim attribute. So print a.ndim. If we pass in a list of lists into a NumPy array, we create a multi-dimensional array, for instance, a matrix. So here I'll say b equals np.array, and I'm going to create a list, and inside of it I'll pass 2 other lists. So 1, 2, 3 is the first list, and 4, 5, 6 is the second list. And let's look at b. So we can print out the length of each dimension by calling the shape attribute, which returns a tuple, so b.shape. And we can also check the type of items in the array, so a.dtype. Now, beside integers, floats are also accepted in NumPy arrays. So c equals np.array, and we could just put in some floating point numbers here, 2.2, maybe 5, maybe 1.1, and let's do c.dtype.name. All right, so let's look at the data in our array. So c. Note that NumPy automatically converts integers like 5 up to floats since there's no loss of precision. NumPy will try and give you the best data type format possible to keep your data types homogeneous, which means that they're all the same in the array. Sometimes we know the shape of an array that we want to create, but not what we want to be in it. NumPy offers several functions to create arrays with initial placeholders, such as zeros or ones. Let's create two arrays, both the same shape, but with different filler values. So I'm going to say d equals np.zeros, and I'll give it a shape of 2, 3, and we'll print d. And then e equals np.ones, and we'll give it the same shape, 2, 3, and print e. And there we can see our arrays. We can also generate an array with random numbers. So np.random.rand, and we give it a shape, 2, 3. You'll see zeros, ones, and rand used quite often to create example arrays, especially in Stack Overflow posts and other discussion forums. We can also create a sequence of numbers in an array with the arrange function. The first argument is the starting bound, and the second argument is the ending bound, and the third argument is the difference between each consecutive number. So let's create an array of every even number from 10 inclusive to 50 exclusive. So f equals np.arrange. We're going to start at 10. We're going to end at 50. Remember, this is exclusive, and we're going to jump by 2's. And let's look at f. If we want to generate a sequence of floats, we use something called linspace. In this function, the third argument isn't the difference between two numbers, but it's the total number of items that you want to generate. So you want to watch out for that. So np.linspace 0 to 15. And what this really means is we want 15 numbers from 0 inclusive to 2 inclusive. So we can do many things on arrays, such as mathematical manipulation, addition, subtraction, square, exponents, as well as Boolean arrays, which are binary values. And we can also do matrix manipulation, such as product, transpose, inverse, and so forth. So let's see some of these. Arithmetic operators on arrays apply element-wise. So let's create a couple of arrays. I'll create A is np.array. I'll just pass in a list, 10, 20, 30, 40. And then B, we'll do np.array 1, 2, 3, and 4. Now, let's look at A minus B. So C is equal to A minus B. And let's look at A times B. So D equals A times B. So with arithmetic manipulation, we can convert current data to the way we want it to be. So here's a real-world problem that I face. I moved down to the United States about 6 years ago from Canada. In Canada, we use Celsius for temperatures, and my wife still hasn't converted to the US system, which uses Fahrenheit. With Numpy, I could easily convert a number of Fahrenheit values, say the weather forecast, to Celsius for her. So let's create an array of typical Ann Arbor winter Fahrenheit values. So Fahrenheit equals np.array, and sometimes it'll be 0 degrees Fahrenheit, maybe minus 10, minus 5, minus 15, or 0. These are not atypical Ann Arbor winter values. And the formula for conversion is the temperature in Fahrenheit minus 32 times 5 over 9, and this gives you the temperature in Celsius. So we'll just say Celsius equals Fahrenheit minus 31 times 5 over 9, and let's look at Celsius. Okay, great. So now she knows it's a little chilly outside this week, but it's not so bad. Another useful and important manipulation is the Boolean array. We can apply an operator on an array, and a Boolean array will be returned for any element in the original, with true being emitted if it meets the condition. For instance, if we want to get a Boolean array to check the Celsius degrees that are greater than minus 20 degrees, we would just say Celsius is greater than minus 20. And there's our Boolean array, true, false, 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 and true. Here's another example. We could use the modulus operator to check numbers in an array to see if they're even. So Celsius mod 2 equals 0. Beside element-wise manipulation, it's important to know that Numpy supports matrix manipulation. Let's look at the matrix product. If we wanted to do element-wise product, we use the asterisk sign. So A equals np.array, we'll create an array here, and B equals np.array, we'll create it. And let's print out the product of A times B. If we want to do the matrix product, we're going to use the @ sign instead of the asterisk. So the asterisk is for element-wise, and this is really important actually. The asterisk is for element-wise, and you can think of just the default as element-wise comparisons or modifications, but the @ sign is going to use the dot product. So we'll print A at B. So you don't have to worry about complex matrix operations for this course, but it's important to know that Numpy is the underpinning of scientific computing libraries in Python. and that it's capable of doing both element-wise operations, so the asterisk, as well as matrix-level operations, so the @ sign. And there's more on this in subsequent courses. So a few more linear algebra concepts are worth layering in here. You might recall that the product of two matrices is only plausible when the inner dimensions of the two matrices are the same. The dimensions refer to the number of elements, both horizontal and vertical, in the rendered matrices that you've been seeing here. So we can use Numpy to quickly see the shape of the matrix. So a dot shape, for instance, will give us, this one was a 2x2 matrix. When manipulating arrays of different types, the type of the resulting array will correspond to the more general of the two types. And this is called upcasting. And you saw an example of that before, but let's see another one. So let's create an array of integers. So array 1 equals np.array. We'll do 1, 2, 3, and 4, 5, 6. And let's print out its data type to make sure that it's actually integers. Now let's create an array of floats. So array 2 equals np.array. 7.1, 8.2, 9.1, and then we'll give it a second list, 10.4, 11.2, and 12.3. And let's print out its data type. So integers, int, are whole numbers only, and floating point numbers, float, can have a whole number portion and a decimal portion. The 64 in this example refers to the number of bits that the operating system is reserving to represent the number, which determines the size or the precision of the numbers that can be represented. So let's do addition for the two arrays. So array 3 is equal to array 1 plus array 2, and we'll print array 3, and then we'll print array 3 dtype. So notice how the items in the resulting arrays have been upcast into floating point numbers. Now, NumPy arrays also have an interesting aggregation functions on them, such as sum, max, min, and mean. So we can print out array 3 sum, array 3 max, array 3 min, and let's try array 3 mean. For two-dimensional arrays, we could do the same thing for each row or column. So let's create an array with 15 elements, ranging from 1 to 15, with a dimension of 3 by 5. So b equals np.arrange 1, 16, and 1, and we're going to reshape this immediately to 3 by 5, and let's print b. Now, we often think about two-dimensional arrays being made up of rows and columns, but you can also think of these arrays as just giant ordered lists of numbers, and the shape of the array, the number of rows and columns, is just an abstraction that we have for a particular purpose. Actually, this is exactly how basic images are stored in computer environments. So let's take a look at an example and see how NumPy comes into play in something like images. For this demonstration, I'm going to use the Python imaging library, PIL, and a function to display images in the Jupyter notebook. So from PIL, import image, and from ipython.display, import display. And let's just look at the image that I'm going to talk about. So I'm just going to open this image called chris.tiff and display this image. Now, we can convert this PIL image to a NumPy array. So array equals np.array, and we just pass in the PIL image. And we're going to print array.shape. And then let's look at array. So we see the shape is 200 by 200. And then we see the values are all uints 8. The uint means that they're unsigned integers, so there's no negative numbers. And the 8 means 8 bits per byte. This means that each value can be up to 2 by 2 by, well, 2 to the 8, 256 in size. But it's actually only 255 because we start at 0, right? That's computer science. For black and white images, black is stored as 0 and white is stored as 255. So if we just wanted to invert this image, we could just use the NumPy array to do so. Okay, so let's create an array the same shape. So I'm going to create a mask, I'll call it, an np.full. And array.shape. So I want it the same as our existing array, but I want it to be full of 255 valued uints. Let's take a look at mask. Okay, so this is like zeros or ones, but full basically lets you set the value that you want everywhere. Now let's subtract that from the modified array. So we'll create a modified array, we'll take our main array, and we'll subtract the mask from it. Remember, this is going to do element-wise subtraction. So all of the values in an array, let's say first value is 100 minus mask, 255, means that we'll be left with negative 155 in that cell, and we're going to do that for all cells in the array. And let's just convert all of the negative values to positive values. So modified array is equal to modified array times -1. So it's going to take that -1 and do, again, element-wise multiplication. So -1 times the first cell, -1 times the second cell, and so forth. And as a last step, let's tell NumPy to set the value of the data type correctly. So we're going to say modified array is equal to modified array.asType. So this is going to tell NumPy, no, you should really trust us. We know what the data type is in here. And we're going to say np.uint8. And let's look at modified array. All right, so that looks maybe as we expect. Lastly, let's display this new array. So we can do this using the fromArray function in the Python imaging library to convert the NumPy array into an object that Jupyter can render. So display image.fromArray modified array. Cool. Okay, remember how I started talking about how this could just be thought of as a giant array of bytes and that shape was an abstraction? Well, we could just decide to reshape the array and still try and render it. PIL is interpreting the individual rows as lines, so we can change the number of lines and columns if we want to. So what do you think that would look like? Well, let's take a look. So we'll create something new, reshaped equals np.reshape, and we're going to take our modified array. So this is just our array from above before we've done the inversion. And we're going to reshape it to 100 by 400. Now remember, it was 200 by 200. So we're changing both the width and the height here, but we're keeping the total number of cells the same. And let's print out, just to convince ourselves that we've actually changed it, the reshaped shape, and then let's display it in line. All right, so I can't say I find that particularly flattering. By reshaping the array to be only 100 rows high but 400 columns, we've essentially doubled the image by taking every other line and stacking them out in width. And this makes the image look more stretched out too, and maybe adds a little bit of weight to me. So this isn't an image manipulation course, but the point was to show you that these NumPy arrays are really just abstractions on top of data, and that data has an underlying format, in this case uint8. But further, we can build abstractions on top of that, such as computer code, which renders a byte as either black or white, which has meaning to people. And in some ways, this whole degree is about data and the abstractions that we can build on top of that data, from individual byte representations through to complex neural networks of functions or interactive visualizations. Your role as a data scientist is to understand what the data means, its context in a collection, and to transform it into a different representation to be used for sense-making. Okay, let's get back to the mechanics of NumPy. So indexing, slicing, and iterating are extremely important for data manipulation and analysis because these techniques allow us to select data based on conditions and copy or update the data. So first, we're going to look at integer indexing. A one-dimensional array works in similar ways to a list. To get an element in a one-dimensional array, we just use an offset index. So we'll create some array, a bunch of elements, and then we'll say a sub 2, and we get the value 5 out. For multi-dimensional arrays, we need to use integer array indexing. So let's create a new multi-dimensional array. So we'll create this one 2 by 3, and let's look at A. If we want to select one certain element, we can do so by entering the index, which is comprised of two integers, the first being the row and the second being the column. So a sub 1, comma 1. Remember, in Python, we're starting at 0. All right, so there's the value of 4. If we want to get multiple elements, for example, 1, 4, and 6, and put them into a one-dimensional array, we can enter the indices directly into the array function. So we can create some new array, np.array, and in that we're going to pass it a list, and from that list we're actually taking our other array and plucking out the values that we're interested in. We can also do that using another form of array indexing, which essentially zips the first list and the second list up. So we can take A and we can actually pass it to lists, and it will zip these values up for us. And so we get the 1, 4, and 6. Boolean indexing allows us to select arbitrary elements based on conditions. For example, in the matrix we just talked about, we want to find elements that are greater than 5. So we set up a condition, A greater than 5. So let's just print, what is a greater than 5? This returns a Boolean array showing the values in the corresponding index that are greater than 5. And so here we get a bunch of falses and a bunch of trues. So we can then place this array of Boolean values like a mask over the original array to return a one-dimensional array relating to the true values. So if we do a sub a greater than 5, what's happening here is we'll take the greater than 5 operator, we'll broadcast that, so we'll compare that across all of the elements of A, creating a new matrix, and then we'll apply that as a mask over the outer A and emit the results. So as we can see, this functionality is essential in the Pandas toolkit, which is the bulk of this course, so we'll be using this a lot. So slicing is a way to create a subarray based on the original array. For one-dimensional arrays, slicing works in similar ways to a list. To slice, we use the colon. For instance, if we want to put colon 3 in the indexing brackets, we get the elements from index 0 to index 3. So remember, excluding index 3. So we'll create some array, just numbers 0 through 5. So that's 6 numbers. And then we'll print a sub colon 3. And so we just get the first few elements, the first 3. By putting 2 colon 4 in the brackets, though, we could get elements from index 2 to index 4. So again, excluding index 4. So print a sub 2 colon 4. Instead of just giving us the length now, that will actually give us just those indexes. For multidimensional arrays, it works similarly. Let's see an example. So a equals mp.array, and we're going to create a new list, and in here we're going to put 3 lists in. So let's take a look at this, and we see that we've got 3 rows and 4 columns. So first, if we put one argument in the array, for example, a sub colon 2, then we get all of the elements from the first, the 0th, and the second row, the 1th. If we add another argument to the array, for example, a colon 2, comma, so second argument, 1 colon 3, we're going to get the first 2 rows, but then the second and third column values only. So let's give that a try. So we want all of the first 2 rows, and then we want 1 colon 3. So in multi-dimensional arrays, the first argument is for selecting rows, and the second argument is for selecting columns. It's important to realize that a slice of an array is a view into the same data. This is really important. This is called passing by reference. So modifying the subarray will consequently modify the original array as well. Here I'll change the element at position 0, 0, which is 2, to 50. Then we can see that the value in the original array is changed to 50 as well. So I'm going to create a subarray, and I'm going to just use what we used before. So a sub colon 2, so grab a couple of rows, and then 1 colon 3, so grab a couple of columns. And I'll print out the value of the subarray sub 0, 0. And then I'm going to set that to 50. I'm going to change it to 50, and then we'll print out what the subarray thinks it is, so that should be 50. But then we're actually going to print our original array, so that's a as well. And remember, a here is 0, 1, because we've changed which columns that we've taken out for our subarray. So when we took our subarray and we did 1 colon 3, we got rid of the 0th column in A. So 0 column in subarray is the first, or the 1 column in A. Okay, now that we've learned the essentials of Numpy, let's use it on a couple of data sets. So here we have a very popular data set on wine quality, and we're going to only look at red wines. The data fields include fixed acidity, volatile acids, residual sugars, chlorides, and so forth. The important one here is the alcohol content and the quality. That's how I buy wine anyway. To load a data set into Numpy, we can use the gen_from_text function. We can specify data file name, the delimiter, which is optional, but we often use it, and the number of rows to skip if we have a header row. It's 1 here. So the gen_from_text function has a parameter called dtype for specifying data types for each column, and this parameter is optional. Without specifying the type, all types will be casted and to a more general or precise type, so there will be some inference done. So wines equals np.gen from txt. We'll take in our CSV file, we'll set our delimiter to semicolon, and we're going to skip our header right now, and let's take a look at wines. All right, so a whole bunch of data here about wines. So recall that we can use integer indexing to get a certain column or row. For example, if we wanted to select the fixed acidity column, which is the first column, we could do so by entering the index into the array. Also remember that for multidimensional arrays, the first argument refers to the row and the second argument refers to the column. And if we just give one argument, then we'll get a single dimensional list back. Okay, so all rows are combined, but only the first column from them. That would be print integer 0 for slicing. So wines sub colon, that means we want all rows, right? We haven't given any numbers to that parameter, comma 0. We just want to get the first columns. But if we wanted to get the same values, but we wanted to preserve that they sit in their own rows, we can actually write wines colon, and then the second is 0 colon 1. So take a look at these two statements for a moment before we run them. In the first one, we say we want one column, the 0th column. In the second statement, we say we want all the columns between index 0 and 1, which happens to only be the 0th column because we never include the end. But the result that NumPy gives us after we execute that actually looks different. All the numbers are the same. The first one, though, gives us a single list of numbers, and the second one preserves the general shape that this is a single column. So this is another great example of how the shape of data is actually just an abstraction, which we can layer intentionally on top of the data that we're working with. If we want a range of columns in order, say columns 0 through 3, and recall this means first, second, and third since we start at 0 and we don't include the training index value, we could do that too. So wines subcolon, comma 0, comma 3. And what if we want several non-consecutive columns? Well, we could place the indices of the columns that we want into an array and pass that array as the second argument. So here's an example. We can take wines, we want all rows, so colon, and then our second argument is actually a list of the indexes that we're interested in. So we can also do some basic summarization of this data set. For example, if we wanted to find out the average quality of red wine, we can select the quality column. We could do this in a couple of ways, but the most appropriate is to use the -1 value for the index, as negative numbers mean slicing from the back of a list. And then we just call the aggregation functions on this data. So we could say wines, the first parameter is colon, the second one is -1 because we just want the last column, and then we'll take the mean. And just pause this for a minute and think. Do you understand what the -1 is? So if not, you'll want to revisit some of the basics on Python slicing and string slicing. All right, so 5.6. Let's take a look at another data set, this time on graduate school admissions. So it has fields such as GRE score, TOEFL score, university rating, and so forth. And it has a chance of admission at the end. With this data set, we can do data manipulation and basic analysis to infer what conditions are associated with higher chances of admission. So let's take a look. So we can specify data field names using gen from text as it loads the CSV data. And also we can have NumPy try and infer this type of the column by setting the dtype parameter to none, as we've seen. So graduate admission equals np.gen from text. We're going to load the data from dataset/admissionpredict.csv. We'll set the dtype to none. We're going to set the delimiter here to a comma. We're going to skip our header, and instead we're just going to pass it the actual names of the columns. So I'm going to write them here: serial number, GRE score, TOEFL score, ranking, SOP, letters of recommendation, GPAs, research, and the chance of admissions. And let's take a look at what that graduate admission looks like. So notice that the resulting array is actually a one-dimensional array with 400 tuples in it. So let's look at the shape. It's actually got 400 tuples and it's just one dimension. So we can retrieve a column from the array using the column's name, for example. Let's get the CGPA column and only the first 5 values. So we'll take graduate admission, sub CGPA. So this tells us we only want to get that one column, and then we want to get the first 5 values, so 0:5. So since the GPA in the dataset range from 1 to 10, and in the US it's more common to use a scale of 4, a common task might be to convert the GPA by dividing by 10 and then multiplying by 4. So graduate admission CGPA is equal to the graduate admission sub CGPA divided by 10 times 4. And let's look at the output of like 20 values there. And it's important to keep in mind that we've actually changed now this data, right? So we actually assigned graduate admission sub CGPA. That changes it on the underlying array. So we've normalized this to a 4-point scale. Remember Boolean masking? Well, we can use this to find out how many students have had research experience by creating a Boolean mask and passing it to the array indexing operator. So we'll take the graduate admission sub research, we'll compare that to 1. If it's 1, a true will be admitted, otherwise a false will be admitted. That creates us a mask, which we then pass into graduate admission using the indexing operator. So that will now just emit certain values that are true, and it will not emit all the false values. And then we're just going to calculate the length. And so we just, the len of that array or the len of that, it's just the same as if it were a list. So since we've got the data field chance of admission, which ranges from 0 to 1, we can try and see if students with high chance of admission, let's say 80%, on average have higher GRE scores than those with lower chance of admission, let's say 40%. So first, we're going to use Boolean masking to pull out only those students that we're interested in based on their chance of admission. And then we pull out only their GPA scores, and then we're going to print the mean values. So let's print the values. So we'll take graduate admission sub chance of admit compared to 0.8. We're going to broadcast this out, take the GRE score and look at the mean. And we're going to do the same thing for the 0.4. So take a moment here to reflect. Do you understand what's happening in the calls above? When we do the Boolean masking, we are left with an array with tuples in it still, and NumPy holds underneath this a list of the columns we specified and their name and indexes. And so we could do graduate admission sub chance of admit greater than 0.8. In this case, we're creating the Boolean mask, and then we're applying it to the graduate admission data, and we see that the output is actually still in tuples because there's many different columns being kept here. And this, I think, is a little bit more clear in pandas, which we'll talk about later in this course. So let's also do this with GPA. So I'm just going to copy and paste the above, but I'm going to change the values to GPA. Well, I guess one could have expected this. The GPA and the GRE for students who have a higher chance of being admitted, at least based on our cursory look here, seem to be higher. So that's a bit of a whirlwind tour of NumPy, the core scientific computing library in Python. Now, you're going to see a lot more of this kind of discussion using this library, and we'll be focusing on this in this course on pandas, which is actually built on top of NumPy. Don't worry if this didn't all make sense the first time through. We're going to dig in a lot more over the next couple of weeks with pandas. But it's useful, and the point of this lecture is so that you know that underneath, NumPy is used as a library, and the capabilities of NumPy are available to you within pandas as we go forward. In this lecture, we're going to talk about pattern matching in strings using regular expressions. Regular expressions, or regexes, are written in a condensed formatting language. In general, you can think of regular expression as a pattern which you give to a regex processor with some source data. The processor then parses that source data using the pattern and returns chunks of text back to the data scientist or a programmer for further manipulation. There's really three main reasons you should want to do this: to check whether a pattern exists within some source data, to get all instances of a complex pattern from some source data, or to clean your source data using a pattern generally through string splitting. Regexes are not trivial, but they're foundational technique for data cleaning in data science applications, and a solid understanding of regexes will help you quickly and efficiently manipulate text data for further data science application. Now, you could teach a whole course on regular expressions alone, especially if you wanted to demystify how the regex parsing engine works and efficient mechanisms for parsing text. In this lecture, I want to give you a basic understanding of how regex works. Enough knowledge that, with a little directed sleuthing, you'll be able to make sense of the regex patterns you see others using, and you can build up your own practical knowledge of how to use regexes to improve your data cleaning. By the end of this lecture, you'll be able to understand the basics of regular expressions, how to define patterns for matching, how to apply these patterns to strings, and how to use those strings for those patterns in data processing. Finally, a note that in order to best learn regexes, you need to write regexes. I encourage you to stop the video at any time and try out new patterns or syntaxes you learn. So first we'll import the re module, which is where the Python stores regular expressions library. So import re. There are several main processing functions in re that you might use. The first, match, checks for a string match that is at the beginning of the string and returns a Boolean. Similarly, search checks for a match anywhere in the string and returns a Boolean. Let's create some text for an example. So text, this is a good day. Now let's see if it's a good day or not. So we can do if re.search, look for good, text, and the first parameter here is the pattern. And then we'll print wonderful if good's there, else we'll print alas and a frowny face. So in addition to checking for conditionals, we can segment a string. The work that regex does here is called tokenizing, where the string is separated into substrings based on patterns. Tokenizing is a core activity in natural language processing, which we won't talk much about here, but you'll study in the future. The findAll and split functions will parse the string for us and return chunks. Let's try an example. So text, Amy works diligently, Amy gets good grades, our student Amy is successful. This sounds like a very positive thing. So this is a bit of a fabricated example, but let's split on this all instances of Amy. So re.split, Amy is the pattern we want to match, and text is our text. You'll notice that split has returned an empty string, followed by a number of statements about Amy, all as elements of a list. If we wanted to count how many times we've talked about Amy, we could use findAll. So re.findAll, Amy, and text. Okay, so we've seen that search looks for some pattern and returns a Boolean, that split will use a pattern for creating a list of substrings, and that findAll will look for a pattern and pull out all occurrences. Now, we know how the Python regex API works. Let's talk a little bit more about complex patterns. The regex specification standard defines a markup language to describe patterns in text. Let's start with anchors. Anchors specify the start and/or end of the string that you're trying to match. The caret character means start, and the $ character means end. And if you put caret before a string, it means that the text that the regex processor retrieves must start with the string you specify. For ending, you have to put the $ character after the string. It means that the text regex retrieves must end with the string you specify. Here's an example. So text, Amy works diligently, Amy gets good grades, and our student Amy is successful. Let's see if this begins with Amy. So we can do re.search, and then inside quotes is our pattern, and we'll put caret Amy. So we want to match Amy at the beginning, and then text. Notice that re.search actually returned to us a new object called an rematch object. An RE-match object always has a Boolean value of true, as something was found, so you can always evaluate it in an if statement like we did earlier. The rendering of the match object also tells you what pattern was matched, in this case the word Amy and the location the match was in, as in the span. Let's talk more about patterns and start with character classes. Let's create a string of single learners' grades over a semester in one course across all of their assignments. So grades equals, and I'll just put a string of A's, B's, and C's, no D's for this student. If we want to answer the question how many B's were in the grade list, we could just use B as our pattern. So re.findAll B and grades. And we see that there's 3 here. If we wanted to count the number of A's or B's in the list, we can't use A and B, since this is used to match all A's followed immediately by a B. Instead, we put the characters A and B inside square brackets. So we do re.findAll, and then we do square brackets, A, B, and then pass in grades. And here we can see the whole list of A's and B's that are found. This is called the set operator. You can also include a range of characters which are ordered alphanumerically. For instance, if we want to refer to all lowercase characters, we could use A-Z in the square brackets. Let's build a simple regex to parse out all instances where the student received an A followed by a B or a C. So re.findAll, and then we'll use the set operator with A and the set operator with B-C and pass in the grades. Notice how the AB pattern describes a set of possible characters which could be either A or B, while the A and then followed by the B-C pattern denotes 2 sets of characters which must have been matched back to back. You can write this pattern by using the pipe operator, which means OR. So we could do re.findAll, AB or AC, in quotes directly, as our pattern with grades. We can use the caret with the set operator to negate our results. For instance, if we wanted to parse out only the grades which were not A's, we would do re.findAll, and then we'd use the set operator, this is important, caret A, and grades. And here we only have B's and C's. So note this carefully. The caret was previously matched to the beginning of a string as an anchor point. But inside of the set operator, the caret and its other special characters we'll be talking about, they lose their meaning. And this can be a bit confusing. What do you think the result of this operation would be? So we'll do re.findAll, caret, set operator, then another caret, A, and grades. Just take a minute, look at that, and reflect on what we just talked about, and what do you think it would be? So it's an empty list, because the regex is saying we want to match any value at the beginning of the string which is not an A. And our string starts with an A, so there's no match found. And remember, when you're using the set operator, you're doing character-based matching. So you're matching individual characters in an OR method. Okay, so we talked about anchors and matching to the beginning and end of patterns. And we've talked about characters using sets with the set notation. And we've talked about character negation and how the pipe of character allows us to use OR in our operations. Let's move on to quantifiers. Quantifiers are the number of times you want a pattern to be matched in order to actually count as a match. The most basic quantifier is the expression of E, curly brace, M, N, curly brace, where E is the expression or character we're matching, M is the minimum number of times you want it to be matched, and N is the maximum number of times the item could be matched. Let's use these grades as an example. How many times has this student been on a back-to-back A streak? So we do this with re.findAll, where the character we're interested in is A, so that takes the place of E. Curly brace, we want to have at least 2 of them, so that's our M value of 2, and we'll just have some big value. We'll use 10 here, and we'll pass this in as our grade. So we're using 2 as our min, but 10 as our max. So we see that there were 2 streaks, one where the student had 4 A's and one where they only had 2 A's. We might try and do this using single values and just repeating the pattern. So we might try re.findAll, and then we've got capital A, and we want min and max match of 1 for those, capital A, min and max match of 1 for those, or grades. As you can see, this is different than the first example. The first pattern is looking for a combination of 2 A's, up to 10 A's in a row. So it sees 4 A's as a single streak. The second pattern is looking for 2 A's back to back. So it sees 2 A's followed immediately by 2 more A's. We say that the regex processor begins at the start of the string, and it consumes variables which match patterns as it does. It's important to note that the regex quantifier syntax does not allow you to deviate from the MN pattern. In particular, if you've got an extra space in between the braces, you'll get an empty result. So re.findAll, a brace 2, comma, space 2, we see that that's an empty result. And as we've already seen, if we don't include a quantifier when the default is 1, 1. So re.findAll, we can just use AA if we just want to match 1. Oh, if you have one number in the braces, it's considered to be both the M and the N value. So re.findAll A brace 2, 2 is the min and the max. So using this, we could find a decreasing trend in a student's grades, for instance. So re.findAll, and we'll look for A's, any number of A's. We'll use 10 as a max here as well. B's, any number, C's, any number, and then we'll pass in grades as our string. Now, that's a bit of a hack because we included a maximum that was just arbitrarily large. And there are 3 other quantifiers that are used as shorthand that we could think about using here. An asterisk is used to match 0 or more times, a question mark to match 1 or more times, or a plus sign to match 1 or more times. Let's look at a more complex example and load some data scraped from Wikipedia. So we'll open a data set called FERPA.txt. This is the FERPA article on Wikipedia as a file. And we'll read this into a variable called wiki. And let's just print this out to the screen. So scanning through this document, one of the things we notice is that the headers all have the word edit in braces behind them, or rather square brackets behind them, followed by a new line character. So if we wanted to get a list of all the headers in this article, we could do so using re.findAll. So re.findAll, and then we could say here, well, we're interested in all characters that are lowercase a through z or capital case a through z. And we're interested in somewhere between 1 and 100 of those characters, as long as they're followed by edit. And we have to escape the square braces here, unfortunately, which makes it a little bit messier, but we don't want to move into the set notation. Okay, so that didn't quite work. It got all of the headers, but only the last word of the header, and it really was quite clunky. So let's iteratively improve on this. First, we can use /w to match any letter, including digits and numbers. So if we do re.findAll, and then we want a character, and we want to match /w. So we're not going to worry about the a through z's and the lowercase capital case. We just want any word character, and somewhere between 1 and 100 of those, followed by edit. So this is something new. /w is a meta character, and it indicates a special pattern of any letter or digit. There are actually a number of different meta characters listed in the documentation. For instance, /s matches any whitespace character. Next, there are 3 other quantifiers that we can use which shorten up the curly brace syntax. We can use the asterisk to match 0 or more times, so let's try that. So re.findAll, we want to match any word character any number of times, so we'll just use an asterisk, so this removes our top 100 limit, followed by edit. Now that we've shortened the regex, let's improve it a little bit. We can add in spaces using the space character. So we can do re.findAll, and in our set notation, we want to match either word characters or space characters any number of times, followed by edit. Okay, so this gets us a list of section titles in the Wikipedia page. You can now create a list of titles by iterating through this and applying another regex. So it's quite common to do, for instance, for title in re.findAll, we put in our regex, which is matching all of the titles. And now we're going to take the intermediate result and split on the square bracket and just take the first result. So we'll just print re.split, and then we'll search, and the character we're looking for is a square bracket, so we have to escape it, so it looks a little nasty. And then we just want to take the first value of this list, which will be the actual title. Okay, this works, but it's a bit of a pain. To this point, we've been talking about regex as a single pattern which is matched. But you can actually match different patterns, called groups, at the same time, and then refer to these groups later as you want to. To group patterns together, you use parentheses, which is actually pretty natural. So let's rewrite our findAll using groups. So re.findAll, and then we start our pattern string, and we want the first group, so first parentheses, will be the first part of our pattern, so that would be any word character or space any number of times. And the second group will actually just be this edit tag that denotes to us that it's a header. Nice. We see that the Python RE module breaks out the result group by group. And we can actually refer to groups by number as well with the match objects that are returned. But how do we get back a list of match objects? Thus far, we've seen that findAll returns strings and search and match return individual match objects. But what do we do if we want a list of match objects? In this case, we use the function findIter. So for item in re.findIter, and then we pass it in this pattern that we're interested in. And then we can print item.groups. And so this is the groups for a specific match item, and we're iterating over all of them. So we see here that the groups method returns a tuple of the group. We can get an individual group using group subnumber, where group sub 0 is the whole match, and the other number is the portion of the match we were interested in. In this case, we want group sub 1. So we don't want the whole match, we want the first item in the match. So for item in re.findIter, so we'll pass in our white space or word character any number of times as the first group, and edit as the second group, and we'll just print out item.group and parameter 1. One more piece to regex groups that I rarely use but is a good idea is labeling or naming groups. In the previous example, I showed you how you can use the position of the group. But giving them a label and looking at the results as a dictionary is actually pretty useful. And for that, we use this syntax where we have parentheses, then a question mark, a capital P, and then the name inside of these angle brackets. Where the parentheses starts the group, the question mark capital P indicates that this is an extension to basic regexes, and the name in the angle brackets is the dictionary key that we use, and it's wrapped in those angle brackets. So for item in re.findIter, we could use as our pattern our first group, so parentheses. We want to name it, so question mark P, and I'll name this title, so you see that we keep these angle brackets. And then we actually put our pattern. So we want the set operator, which indicates character matching, and we want to do any word, so slash W, any word character, as well as spaces. So we'll put the space in there any number of times. So we've got an asterisk for that. Then the second group, we want to name this as well, question mark P, and we'll call this edit link for lack of a better word, and then our pattern here, which we have to escape the square brackets. So we can get the dictionary return for the item using the .groupDict. So print item.groupDict. This is a dictionary, so we can just do subtitle, which is our key. Of course, we could print out the whole dictionary for the item too and see that the edit string is still in there. So here's the dictionary kept for the very last match. So print item.groupDict, and there's our actual full dictionary. Okay, so we've seen how we can match individual character patterns with the set operator, how we can group matches together using parentheses, and how we can use quantifiers such as asterisk, question mark, or m brace n to describe patterns. Something I glossed over in the previous example was /W, which stands for any word character. And so there are a number of shorthands that can be used with regexes for different kinds of characters, including a period for any single character, which is not a new line, a /D for any digit, and /S for any white space character, like spaces and tabs. And there are more, and a full list can be found in the Python documentation for regexes. One more concept to be familiar with is called look ahead and look behind matching. In this case, the pattern being matched to the regex engine is for the text either before or after the text that we're actually trying to isolate. For example, in our headers, we want to isolate the text which comes before the edit rendering. But we actually don't care about the edit text itself. Thus far, we've been throwing the edit away. But if we want to use them to match but don't want to capture them, we could put them in a group and use look ahead instead with the == syntax. So let's see an example of this. For item in re.findIter, we're going to match two groups. The first group is going to be a named group called title, and we're just copying that from before. But the second group is actually one of these throwaway groups that is look ahead. So we're just looking for edit, but we're actually not matching on it. So what this regex says is to match two groups. The first will be named and called title, and we'll have any amount of white space or regular word characters. And the second will be the characters edit, but we don't actually want this item put in our output match objects. And so we can print that item. And we see that we have 3 match objects there, their spans, and the actual values that they matched. Let's look at some more Wikipedia data. Here's some data on universities in the US which are Buddhist-based. So with open from datasets, buddhist.txt as file, and we'll read this into a variable called wiki. And for good measure, let's print this variable output to the screen. We can see that each university follows a fairly similar pattern, with the name followed by an M dash, then the words located in, followed by the city and the state. I'm actually going to use this example to show you the verbose mode of Python regexes. The verbose mode allows you to write multi-line regexes and increases readability. For this mode, we have to explicitly indicate all whitespace characters, either by prepending them with a slash or by using the /s special value. However, this means that we can write our regex a bit more like code, and we can even include comments with the pound sign. So pattern equals, and we'll use this triple quoted string, which means we can go on multiple lines. So the first group we want to match is the title. And so here I'm going to say I want it to be a named group called title, and I want any number of characters. And so I'll just use .star. And we'll add a comment, the university title. The next group is going to be a space, or sorry, the M dash followed by a space, so I'm escaping that in this case, located, space, in, space. So this is just some indicator of the location. And I don't care about this, so I'm not naming this group. The next one we'll make is the named group city, and this is any number of word characters. And so this is the city that the university is in. Then we have some separator, comma, space that we see is a common pattern, and I don't care about these, so I won't name this group. And then we'll name another group the state, and it's just like city, any number of word characters, so the state the city is in. And then we'll end the triple quoted string. So now when we call findIter, we just pass the re.verbose flag as the last parameter. And this makes it much easier to understand large regexes. So we just use this like previous, and we say for item in re.findIter, we pass in the pattern, we pass in our source text, but because it's this multi-line verbose mode, we say re.verbose to let the processor know. And we can get the dictionary returned to us for the item with the .groupDict value. So we print item.groupDict. And so there we see our output is a set of universities, their cities and their states, and all of the groups that we didn't name are just, they're matched, so they're consumed by the processor, but they're thrown away. Here's another example from the New York Times, which covers health tweets on news items. This data came out of the UC Irvine Machine Learning Repository, which is a great source of different kinds of data. So with open datasets, New York Times health.txt as file, and we'll read everything into a variable and take a look at it. So health equals file.read, and we'll look at health. So that's a lot of tweet data. So here we can see there are tweets, and the fields are separated by pipes. Let's try and get a list of all of the hashtags that are included in this data. Now in Twitter, a hashtag begins with a £, or the hash mark, and continues until some white space is found. So let's create a pattern. We want to include the hash sign first, then any number of alphanumeric characters, and we end when we see some white space. So our pattern is equal to the hash mark, followed by word characters or digits, and an asterisk, any number of those. And then we'll use a look ahead, just looking for any white space. So we'll use /s in this case. We could have used a space if we weren't worried about tabs and so forth. Notice that the ending is a look ahead, because we're not actually interested in matching this white space and returning the value. And also notice that I used an asterisk instead of the plus for matching of alphabetical characters or digits, because a plus would require at least one of each. So let's search and display all of the hashtags. So re.findall, pattern, and health. So we can see that here there are lots of Ebola-related tweets in this particular data set. This lecture has been an overview of regular expressions, and really we've just scratched the surface of what you can do. Now, I actually find regexes really frustrating. They're incredibly powerful, but if you don't use them for a while, you're left grasping for memory of some of the details, especially named groups and look-ahead searches. But there are lots of great examples and reference guides on the web, including the Python documentation for regex. And with these in hand, you should be able to write concise and readable code which performs well too. Having basic regex literacy is a core skill for applied data scientists.